Hello everyone, welcome to the lecture for thermal physics. I hope you all had a good break during the Thanksgiving weekend. This lecture is going to substitute for the lecture on Tuesday in class, right? November 30th for thermal physics. As you all might be anyway attending the capstone talks, and I certainly am going to miss the capstone talks because I am on travel to a conference. But please make sure everyone watches this video before the class on Thursday. It is important because I will continue after I left off in these two lecture videos. So let's start. Today we want to look at rotation of diatomic molecules. Keep in mind, what is the goal here? Our goal here is to now somehow understand the application of Boltzmann factors. B factors is my acronym for Boltzmann factors and average values. If you all remember, we studied some of these things in the class by focusing on simpler examples. I started with something on harmonic oscillator, right? Now let's take a look at a little bit more complex system. What I have drawn here is the rotational states of a diatomic molecule. We need help from quantum mechanics at this point, right? What are we going to assume? Let's take a note down a few assumptions, right? Assume isolated diatomic molecule think of a low density gas, right? Low density gas. And the molecule, it could be pretty much, let's say, such as carbon monoxide, CO, right? Two different atoms. Or let's say hydrogen chloride, HCl. Two different atoms at the edges, right? What we have is from quantum mechanics. Anyone interested further, take a look at the appendix. What you do have here is quantized level for rotational energies of a diatomic molecule. You all know what quantized means, right? Discrete. Only certain values are allowable, right? In this case, we are given the energy of such a case is E of J is equal to J times J plus 1 times E. What is J here? J here is equal to 0, 1, 2, and so on, right? These are any particular values of J. E, I'm just going to call this E or a constant. This constant actually has a fundamental meaning. This E is inversely proportional to the molecules I. You all know moment of inertia? Molecules moment of inertia. Rotation, right? You understand all that, right? Think about this as x prime square over 2i. In this system, the degeneracy, you all understand degeneracy as well, I believe, right? In this case, the degeneracy for level J is given by n of J is equal to 2J plus 1. That is what actually you are seeing here in the energy diagram. 2J plus 1, J equal to 0 gives me 1, J equal to 1 gives us 3, J equal to 2 gives us 5 degenerates, and so on. You go to the next number and you will see the number changes, and you keep going on, right? J equal to 3, you're going to have something like 12E. That's your constant value that keeps adding to this case. What's our goal? Our goal is now actually, think about this. Our goal is to somehow understand how are we going to also apply our knowledge of partition function. So let's first quickly put down the partition function for a case like this. Writing partition function as a sum over J. Let's do that. What are you going to end up with? Over here you got Z rotational. Z rotational, ROT subscript is for the rotational states of a diatomic molecule, right? In this case, is going to be equal to sum over all the value from J equal to 0 to infinity. You all know now we need that degeneracy factor in front. If you all remember, I did an example in the class for the hydrogen atom, and we did put the degeneracy in the front, right? It was like 4 states or something versus the ground state, something like that. So over here, you need that as well. So now this is the degeneracy. Then you add e raised to minus E of J over KBT. If I plug the value, we already given the energy of the system. If I plug the value, what I'm in principle doing is I'm going to replace some of, not some, this quantity by the energy of the system. And let me do that now. This is going to be equal to summation J equal to 0 to infinity 2J plus 1. Multiply the whole thing by e raised to minus J times J plus 1 E over KBT. That pretty much gives you the partition function for this system. You remember partition function, what is it going to do for us? It's always going to estimate the number of states, that are allowed, right? That are possible for in that case. That's what we have done here. And in this is, if this is confusing, this is E, right? All I have done is actually replaced this equation right here for E of J into this term here, e raised to minus EJ. That's all I have actually done. The degeneracy factor stays here. Everything can stay, in the same equation. Now, what does this do? What does this do is somehow we need to now understand how are these different states distributed. Also, we can take a look here. This looks like a, partition function. You can actually sum over all the states. The states over here, the number of degenerate states and the total states, they can be a lot of values, right? There is no way actually to just so that there is no way to evaluate the sum exactly. But what we can do is we can actually evaluate the sum numerically for any particular temperature, right? We all know partition function does depend on the temperature, right? So it can depend on the temperature. In this case, we can actually approximate the sum as an integral. Keep in mind, now we are going to make a conversion from a sum to an integral. It always makes our life easy. And we can do that if the states are, so let me now remove this sheet. Hopefully you all had a chance to write whatever you needed from this one. And I'm going to keep this. The next one is the figure which is over here. What I'm trying to do here, what is the goal here? This is actually now a pictorial depiction of the sum as the area under a bar graph. You can all see the bar graph, and I have just truncated here. In the book you might see the case might probably go until, I don't know, 14 or 20 or something. I truncated here to 8, right? What you can do is you can set this value, you can set the energy scale for this particular case, right? And our goal is either evaluate numerically or approximate. Keep in mind, we are interested in temperatures much higher than, let's write that down. We are interested in temperatures, and I'm going to call this T's, temperatures much higher than over KB. So the quantity KBT over E will be much greater than 1. Keep in mind, E here is very small, right? For a CO molecule, for example, for instance, E is equal to 0.00024 eV. So it's almost like E over KBT is going to be 2.8 kelvins or something. Ordinarily, we are interested in temperatures much higher than E over KBT, and that's the reason. And in this case, what happens is the number of terms that contribute significantly to the partition function will be quite large. Really large number, right? And as a result, what we are going to do? Well, we can approximate the sum, that means the partition function, by an integral under the curve at a particular high temperature, right? Let's put that down. What we can do, we can approximate the sum. In this case, the sum is what? The partition function, which is very large, by integral, as I said earlier, under the curve. Take a look at the curve I have here. Somehow, if the states are close enough, and if you have infinitely many states, you can actually draw a smooth curve, right? And that curve, area under the curve, is literally going to give us that value, right? Area under the curve at high T. Very small BE, right? Very small BE in this case. From here, what we are going to do? Well, now we are in a position to write down, and take a look here. What I have done is actually just multiplied and divided by delta J on both the sides. This will allow me to integrate with respect to D of J. This delta J, I'm just going to replace this with D of J. That is going to help us now to somehow convert this into an integral, right? So let's write down. This point, Z rotational is going to be approximately equal to 0 to infinity, right? 0 to infinity, 2j plus 1 e raised to minus j times j plus 1 beta e. Don't forget beta, we did write this down earlier in the past, as 1 over kBt. Just in short form so that it's always easier to take derivatives, or in this case, even the integral, right? This is our form now, and in the last, we still have d of j left over. At this point, what you need is, now we need to take out this, this integral and calculate the value, right? I'm assuming you all know the substitution you can make for such cases. It always makes life easy, right? So let's put that here. Let's do the substitution and let's write that down. I'm going to probably put a couple of steps in the next page as well. But what is the substitution? Well, you can let u is equal to j times j plus 1. That means du is going to be equal to 2j plus 1 d of j. This makes sense, right? This is j square plus j. U is literally j square plus j. As a result, if you differentiate that, du is going to be j square is going to be 2j, and the other j is 1 dj. Plug this value, substitute this value in this equation here. Let's do that. I'm going to leave this for a second here, so in case anyone is writing along with the lecture, that will help you actually anyway. Once you have that, let's carry out the integral. I'm assuming you all have taken such integrals fairly easily in the physics curriculum, and you'll be fine here. So let's do that. Now what we need, therefore, z rotational is going to be equal to 0 to infinity, summing over all the states, right? In this case, the integral is converted from 0 to infinity to all the states. E raised to minus u be times du. Once you have that, this is going to be equal to minus 1 over be, e raised to minus u be, and put the limits. 0 to infinity, right? Therefore, Z rotational is going to be equal to 0 minus 1 upon beta E. This term, everything from here is going to go out. 0, e raised to 0 is going to convert to 1, and you got minus 1 upon BE. And when you do the math here, just one more step, what you get here is 1 over BE. If I replace the value or put back the value for beta, we end up getting KBT over E. And over here, one condition is for KBT, very, very large. And in this case, what will happen is, this result actually is what? Valid, I would say, or applies in the high temperature limit, where the Z rotational, the partition function for the rotational states, is quite large than 1. And don't forget over here, Z increases with increasing temperature. Take a look. Take a look at the partition function value. From here, fall back to a problem we also did in the class for the harmonic oscillator, and we actually went ahead and did the, used the formula. Actually, we also derived a formula which helped us to get the average values, right? And in this case, average value for the rotational energy. Let's put that down here. In the high temperature limit, in the high T limit, we can calculate average rotational energy. You know my way of writing this. You can also write this with E and dash above it, right? And this is a, go back to our previous notes and you will see one of the forms we can use. There is another one. If you want, I can even try that out. We can try through either definition and it will work. Minus 1 over Z, take the derivative of Z with respect to beta. That's what it tells us. In this case, all we need is, this is going to be equal to minus 1 over Z, 1 over BE is going to give us this BE. Minus style still says. And when you differentiate this, this is in the, don't forget, this is over here in the beta. Sorry, beta is in the denominator. So put that in here, minus 1 over, yes, this will become square times E, right? Solve for there. This is going to cancel out. Minus signs go out. You end up with 1 over beta, or if you will, this is KBT. I'm hoping this result will also ring a bell. There's something like this you did in the past. What is this? The average rotational energy, KBT. This is, I would say, pretty much, this is the prediction of equipartition theorem. Why? Think about, I hope you all remember what we needed for calculating, the average energy using the equipartition theorem. If you all remember, we always needed the rotational degree of freedom. And in this case, diatomic molecule has 2 rotational. I'm only talking about rotational. Do not get confused here. I'm not going to any other modes. 2 rotational degrees of freedom. This pretty much confirms that our way of doing this, by using the advantage of knowing the Boltzmann factors and understanding partition function, we can also calculate the average rotational energy, in this case for a diatomic molecule, right? So this is fascinating. You can actually now deal with really, really complex systems. Think about that. You can apply this, and even from here, I can take one more step here. Actually, if I wanted, I could take one more step here and put down the heat capacity. What will be the heat capacity? Heat capacity You all know C is going to be given by change in energy, in this case the rotational, by change in temperature. If I differentiate this by with respect to temperature, all that is left is Kb. That is the heat capacity for this case. My point is, this recipe also allows you to calculate a lot of different important quantities, and you can actually, work with more complex systems. Don't forget, using our previous understanding, it's not always trivial to treat a system like rotation of a diatomic molecule. Why? Because we need to invoke quantum mechanics also here and try to make sure we are calculating every single microstate, right? Another way, I use this formula. I always try to do this quickly. So let me do there is another way to reach the same result. And as you all know, the second formula, which I can, or you all can use, is also using the other expression. In this case, what was the other expression? E rotational can also be given as minus of derivative of beta with respect to beta for logarithm of C, logarithm of the partition function. Plug that value in. This is going to be equal to minus ln 1 over BE. This is going to be equal to logarithm. I'm just inverting to get rid of the negative sign in front here. Inverted the logarithm, right? This should be one-step process. You get the value here. It should be 1 over BE, but this E still needs to be different there after differentiation. So it's going to be equal to 1 over B, or alternatively written as KBT, because beta is 1 over KBT. Still get the same answer. My point is, you can, if you are asked in an exam, you can choose your formula, either one, and try to help us. Get that answer, you'll be fine, right? Interesting result. Interesting result because something we used in the equipartition theorem in the past, all the way probably at the start of the semester. And something like over here now we can do with more advanced knowledge of a little bit of quantum mechanics and understanding of partition function. So much for same, different type of molecule, right? When I say different type of molecule, let me quickly draw here. What I meant was C and O. Obviously C and O, one could be carbon, one could be oxygen. They have two different types, right? They're bonded. What about similar type? Identical. What about identical, let's say a molecule like O2 in this case, or N2 if I want. Oxygen and oxygen. What about O2 molecule? What about N2 molecule? In this case, can we use the same understanding? Are we going to calculate the same number of states, or how are we going to incorporate? Because what happens is, think about this. For a molecule like which are symmetric, over here 180 degree transition on swapping them is not going to change the state. So we are almost double counting. I need to insert a value of half in this equation, right? If I'm asking you, what about, if this was a class, I would have definitely waited for all your responses to see where we are going with this. Diabatic molecules with identical atoms. Can we still apply the same understanding like O2 or N2 or something like that, right? In high temperature limit, when Z is quite large than 1, then in this case, what we do is we conveniently put the rotational partition function as KBT over 2E. All I have done is inserted factor of 1/2 in Z. Don't forget, this does not change anything. You can't possibly think that, okay, once we have this change, maybe equipartition or the formula we used here will change the values for energy. It will not, right? Let's try that out. For example, therefore, let's say E rotational for a case like this, for a molecule like this, is going to still be equal to -1 over Z I'm just going to use the first one, the first relationship. The second, I'm not going to worry. I'll assume you all will take care of that. I can write this down as 2BE 1 over 2BE. All I have done is replace the value for the partition function. Over here it was 1 over z, so I have inverted that value, and I have already written KBT, 1 over KBT in terms of beta here. Once you do this, the answer you get is what? Minus 2BE still stays, obviously, and you're differentiating this with respect to beta. It's in the denominator. It's going to become 2 beta square E, and the minus sign will come in. If you solve this, you end up with 1 over beta, which is again equal to KBT. Nothing has changed. Think about this. It does not change the value. Right? The overall over here for identical atoms, the factor of half actually cancels out of the average energy. So it has actually, if you go ahead and calculate the heat capacity from here on, absolutely no effect. And as a result, you have, make sure you understand what recipe to use when you're calculating a rotational energy for a system like this, average. Specifically using, you can calculate, if you have some previous understanding, you can do that with a different route. But over here, we are strictly focusing on understanding or computing the partition function and calculating the values from there on. I'm hoping this portion is clear. I would like to continue now here. So far, just so that so far, and there is a problem which I'll keep in the notes. It's rather trivial. I think 6.25. I'll keep it in the notes, and you can actually, symmetry of the CO2 molecule and the rotation, you are supposed to calculate the partition, the rotational partition function for CO2 molecule. Try it out on your own. Take a look at the notes after that. You'll see it's a one-step process. You all will be fairly comfortable doing that, okay? One thing we have not done so far is, if you all remember, in the past, some student even asked that to me, that we have never derived the equipartition theorem. I believe this is the right time. It's the right time to understand the equipartition theorem. And I think this is, so here's my plan. My plan is to make actually 3 videos of roughly, 25 to 30 minutes. So this is, I believe, I'm going to take a pause here, cut this video down here. I'm going to make the next video, which will again start from equipartition theorem, so that there are like 3 videos with, similar time that you can utilize for the missed class, okay? So thank you. Look back, go back again now to the next video, which I'll prepare and upload.